Let's look at this problem here. We have a uniform 2 kilogram circular disc with radius of 20 centimeters rotating clockwise about an axis through its center. Okay, I'm going to kind of sketch this to the side. So M1 is 2 kilograms, radius 1, 20 centimeters. It's rotating clockwise about its axis through its center with an angular speed of 30 revolutions per second. A second uniform disk that is not rotating is dropped onto the first disk. So we have a second disk, M2 1.5 kilograms, radius 15 centimeters. It is not rotating initially, but it is dropped onto the first disk so that the axis of rotation of the first disk passes through the center of the second disk. We want the final angular speed of the two disks when they are rotating together. All right, so we have disk 2 is not rotating. It's dropped onto disk 1. There will be friction between them that ends up getting them both just rotating together as one big object. And we want to find that angular speed. All right, I see a collision here. Disk 2 collides with disk 1. So a collision, I want to jump to conservation of angular momentum for the system, meaning L of object 1 initially plus L of object 2 initially is going to be L of the system finally. They're stuck together. Okay. So L is I times omega. The I of either disk is not changing individually. The disks individually have their same mass, their same radius. So when I write L1, I'm going to say just I1. It doesn't need to be I1 initial because I is not changing. I1 omega 1 initial plus I2 omega 2 initial, which we know is 0, has to equal I1 omega final plus I2 omega final. But because they are rotating together, we can factor the omega final out and simply add their i's together. We cannot add their masses together and plug into an equation for moment of inertia. For disks, we know I is 1/2 mr squared. The two disks have different masses, different radii, so we have to calculate their i's individually. And then when we plug it in, our fundamental equation, because omega 2, disk 2 is not rotating initially, all of the angular momentum is what disk 1 has. Finally, because they're rotating with the same angular speed, we can factor out the I1 and I2, the omega final, which leaves us with I1 plus I2. And omega final will simply be I1 omega 1 initial over the sum of those two i's together. So it's similar to what we've done before when we did our collisions and the objects stuck together, we could combine their masses. With rotation, we can't combine their masses, but we can find an overall moment of inertia by adding up the i's. So let's go ahead and plug in. These are both disks, and as I mentioned, You can get this equation off the table, either in the test notes or in the chapter. I1 is going to depend upon the mass of disk 1 and the radius of disk 1. So that is I1. And if you wanted to find those before plugging them in, that would be fine. I2, same equation, but we need the mass of disk 2 and its radius. Turns out the 1/2 will cancel because there's a half in every term. So let's plug in. Excuse me, mass 1 is 2 kilograms. Radius 1 is 2 centimeters, which I'm putting into meters. Now, omega 1 is given in terms of revolutions per second. Ultimately, all this stuff, everything multiplied by omega 1 initial are MR squared. Those units are going to cancel. And so whatever units I leave omega 1 initial in will be the units omega final will be in. So we know omega usually needs to be in terms of radians per second, which we can totally convert easily. Because though of this setup here, the units in the parentheses here are going to cancel. And so I'm going to go ahead and just leave omega 1 initial in terms of revolutions per second. And that's going to give me revolutions per second on omega final. Since the problem is not specifying specific units, it's okay to leave that in revolutions per second. The safe bet, though, is always to convert to radians per second. There's nothing wrong with that either. All right, so M1 is 2, radius of 0.2. M2 is 1.5, radius of 15. You might notice as well, you could leave the radii in centimeters because those would cancel as well. But you do want to be careful just watching your units in general. So plugging these numbers in, I'm getting 21 revolutions per second as the final angular speed of the two disks rotating together. So they've slowed down. Originally, the first disk was rotating at 30 revolutions per second. The system is now rotating at 21, so smaller, which hopefully makes sense because we now have additional mass. There's another disk that was not there before that is rotating on top of the first disk. So the system slowed down because the total moment of inertia of the system went up.